In the future, we will eventually journey to Mars, eagerly anticipating the arrival of this moment. However, what people often overlook is why we should settle on Mars, why we should build cities on this desolate land, rather than merely establishing isolated outposts or homesteads. Today, we will discuss how to establish at least 2 cities on Mars, each with a population exceeding 5,000 people. The question lies in this. Although scientific research on Mars is of significant importance, we lack strong economic incentives to go to Mars. Admittedly, scientific research itself has become a cornerstone of the modern economy. Each year, global investments in science exceed the total GDP of most recent nations. However, these funds are dispersed across various fields, and emerging planetary sciences such as Martian geology and hydrology attract relatively little funding. Mars is often imagined as a manufacturing hub or an industrial planet. Indeed, Mars is rich in resources. Among the terrestrial planets in the solar system, its mass is second only to Earth and Venus, with an abundance of metal reserves. But it resides at the bottom of a gravity well. Elsewhere in the solar system, there are many asteroids rich in metallic resources, including Mars to moons, Phobos and Deimos. We discussed their colonization potential months ago. They are likely asteroids captured by Mars' gravity. Mars' gravity is only slightly shallower than Earth's and Venus's, meaning transporting materials outward from Mars is easier. For this reason, the development and settlement of Mars are almost inevitable. Although asteroids are rich in resources, Mars' mass exceeds the combined mass of all asteroids and even the total mass of all solar system satellites. The 2 largest moons, Ganymede and Titan, are only 1/4 to 1/5 the mass of Mars. Their metal content may be much lower than Mars, but they contain more volatile substances. If we were to deplete all asteroid resources, it might take thousands of years. While this timeline isn't long compared to the time required for terraforming Mars, we still like to imagine cities and nations emerging on Mars within the next few centuries. Even long-standing ancient cities often thrive due to their importance in trade or agriculture. Thus, when discussing Mars' long-term settlement, we must consider the scale of time. Mars' advantage lies in its early days. The spaceport may become the center of migration, unlike previous settlement sites where immigrants quickly moved outward in search of new land after arrival. Mars has no vast wilderness. Workers developing mining areas and resource extraction points may form the primary settlements. If crops are to be grown, it must be done under domes, and with no native soil. All agricultural land must be established through hydroponics or treated Martian regolith. Thus, every location on Mars is almost indistinguishable. Early settlers might choose to build domes near the spaceport, and others might continue constructing next to these domes, forming a continuous cluster of domes. Recent data suggests Mars' geological and hydrological conditions are slightly better than we initially feared. The famous Olympus Mons, the tallest mountain in the solar system, covers an area equivalent to Poland. Its last eruption may have occurred 25 million years ago. We often envision a mass driver launch platform on Mars, using Olympus Mons as a launch ramp to help overcome the challenges of a gravity well. Although Olympus Mons is more than twice the height of Mount Everest, it is not a steep peak. In Mars' low gravity, climbing this mountain is not difficult unless you're wearing a bulky spacesuit. In this scenario, we might even consider building a vacuum train on the mountain or constructing a tall tower at its summit to extend the length of the launch ramp. Due to Mars' low gravity, the atmospheric density decreases more slowly than on Earth. Low pressure and low gravity also make tall tower construction easier. We could extend the launch ramp above the summit, allowing spacecraft to exit the atmosphere from lower pressure. Mars' orbital velocity is about 3.5 kilometers per second, so we may not need much effort to eliminate air resistance from the launch ramp. A bare magnetic levitation track powered by nuclear reactors could accelerate spacecraft to the highest possible speeds. If necessary, spacecraft could use onboard fuel to accelerate further. On Earth, the fuel-to-payload ratio for launching spacecraft into low orbit is about 7 to 1. On Mars, this ratio can be reduced to 4 to 1. If the launch ramp increases the speed to 2.5 kilometers per second, spacecraft would only need to carry fuel equivalent to 1/4 of their mass, comparable to the fuel consumption of cars or airplanes. More importantly, we can produce fuel on Mars. A fuel production facility would be an ideal location for a Martian spaceport, further becoming a focal point for urban development. We can imagine 5 or 6 cities appearing on Mars. They may all have similar goals: as no single nation is likely to monopolize Mars, and there are likely multiple competing development projects. This competition does not have to be adversarial, much like national bases in Antarctica. While there is competition, it is generally cooperative. Similarly, international cooperation in space has a comparable track record. Although not always intimate, it is fundamentally friendly. Fuel is critical to Mars' economic development, even more so than food. Producing both requires water. Thus, like Earth, Martian cities may also be built around water-rich areas. The preferred locations might be near the equator, as Mars is relatively cold, and equatorial regions offer a greater warming advantage. However, to find significant ice resources, settlements might have to move toward Mars' polar regions. Based on these ice resources, we could use energy to convert ice into water, then apply electrolysis technology to split water into hydrogen and oxygen. These are excellent fuels for rockets and conventional vehicles. Methane might be an even better fuel. It is easier to store than hydrogen. Mars is rich in carbon, so we could combine hydrogen obtained through water electrolysis with carbon to produce methane or other more complex yet easily stored hydrocarbons. Like Earth, Martian settlements might cluster around water sources and nitrogen supplies. While Mars' nitrogen resources cannot meet the needs of full-scale terraforming, they are sufficient to support the establishment and growth of multiple cities. Mars' atmosphere, though thin and primarily carbon dioxide, contains only 2% nitrogen. However, the total nitrogen in the Martian atmosphere is about 675 billion tons. Earth's agriculture consumes about 200 million tons of ammonia annually, far less than 1/1000th of Mars' nitrogen reserves. Therefore, even if Martian plants require large amounts of nitrogen, we could continuously extract enough nitrogen from Mars' atmosphere to produce ammonia. This nitrogen might gradually leak back into the atmosphere from settlements. Moreover, the outer solar system's ammonia ice reserves are abundant, which could provide additional nitrogen resources for Mars. Mars' winds enable its thin atmosphere to circulate on the surface, and its carbon dioxide, nitrogen, and trace amounts of argon can be utilized as resources. As long as enough ice can be found, we could use Mars' atmosphere to manufacture materials needed by humans and plants, as well as produce sufficient fuel. Equatorial regions might rely on solar power generation, while polar regions would require orbital space solar energy or nuclear power plants for energy supply. Mars has enough thorium and uranium to support the operation of nuclear power plants. If necessary, Earth could export small amounts of nuclear fuel to Mars. Therefore, Martian settlements are likely to rely on nuclear energy from the start. Depending on the economic feasibility of building solar or nuclear power plants on Mars, settlements could evolve accordingly. If nuclear energy proves economically viable on Mars, it could also benefit more distant planets in the asteroid belt. Martian cities might form around fuel production facilities and launch sites. These could result from collaborations between one or more nations. Such cities would require power plants. Even in equatorial regions relying on solar power, nuclear reactors might be needed as backup power sources. A city of 5,000 people might require tens of megawatts of electricity. Existing small modular nuclear reactor designs are mature enough to be adapted for use on Mars. Rotating residential areas could increase artificial gravity, but I personally believe Mars' gravity is sufficient for humans, plants, and animals. If not, city residential areas might be designed as large domes that rotate to form a bowl-shaped space. Residents could access other areas or exit the city through central axes, via tunnels at the bottom or towers at the top. Such towers might be used to park aircraft, or they could connect nearby cities via underground railways or tunnels. Mars rovers are feasible for surface transportation. Aircraft and helicopters can operate on Mars, but due to the thin atmosphere and lack of oxygen, they usually require electric power or rocket-style fuel and oxidizers. Flight would play a vital role on Mars, especially for long-distance transport between settlements. Large pressurized all-terrain rovers would also be common vehicles. In early Martian cities, large personal vehicles are unlikely. City layouts would prioritize optimizing mass, reducing travel distance within the city. Therefore, most early Martian settlements would develop vertically to minimize the need for transportation. This may change in the future. Terraforming is unnecessary for Martian cities. Self-sufficient cities could theoretically be built on the Moon or other planets. However, due to its proximity to Earth and relatively habitable conditions, Mars will likely become one of the brightest civilizations in the solar system.